Hi, welcome. So the last time we talked about having these current balances, and to calculate our Jacobian, we needed to differentiate these current balances with respect to the voltage at A and the voltage at B. So, okay, let's just draw a resistor, and then I will have A and B here, just for the sake of derivation. Okay, so the current balance at A is called FA. Okay, so how do you do it? Okay, well, the current balance is so I out minus I in. Okay, so I out and I in should balance out. This should be equals to 0. Alright, so FA is the current balance over A, and is the sum of currents out minus sum of currents in. Just a reminder, sum of currents out is by convention positive according to spiceSharp. Okay, so let me open the browser. Okay, spiceSharp, GitHub.io, spiceSharp. Okay, so let's see. Here we are. Let's go to the tutorial. And where are we? You should go to modified nodal analysis, or the resistor example here. Okay, so here's where we are. I think we've gone through this many times, so I'm just repeating it slowly to give context. Yeah, I'd rather repeat it to give it context. So again, what is the contribution of this resistor R to this current balance FA, right? The only contribution by this resistor R to FA is actually this term right here. It contributes to the I out. Okay, that of course is if current is going this way from A to B. Okay, so this is I out, right? I out is the only term that it's has contributed here. Okay, and not the entirety of I out, because you might have many resistors connected to this node. It will just be this current IR, the current flowing through this resistor. So this is I out is equals to IR plus ... So this is a general case where you have many inputs, many outputs. Okay, but for just a resistor connected in series, you only have one output, so that is just convenient. Okay, but often that in general that's not the case, but let's just do it for a general case. So IR is the only contribution to the current balance by this resistor. It's the current flowing through the resistor, and that affects the current balance here. And likewise over here, FB, okay, equals to I out minus I in. And of course note that the I out here is and I in here, all of these are done at the point A, or at the node A, and this one is done at the node B. So the part at the node B is I out minus I in, and the current flowing through this resistor will contribute to the negative term here, okay, minus IR. So this is what's happening right here. Okay, this is what's happening right here. IR, the current flowing through the resistor, contributes to the I out term here. The current flowing through the resistor contributes to the I in term at node B. Okay, so the only thing we have to consider when we do the Jacobian, right? The Jacobian, the only terms we have to consider during the Jacobian are del FA, del VA. Okay, del FA, del VA, del FA, del VB. Okay, because the current over here is dependent on the voltage between A and B, or the delta V here, right? So anyway, yes, so this is the Jacobian that we are doing. So these are the four terms here, quite standard. Okay, let me put it properly. So this is del FB, del VA, and one more, del FB, del VB. Okay, so these are the four terms that we need to sort of figure out. Okay, so what exactly is del FA del VA for this resistor? Okay, for this resistor only. For resistor R, the only thing we actually have to care about is this term, the IR term. So the contribution to del FA del VA for this resistor R, it will be equal to del IR del VA, and okay, del IR del VA del IR del VB. I skipped ahead a little bit, and of course we do the same for the bottom, except we have a sign change, because this IR is now negative, right? So it's negative IR, so I have to put a negative in front and basically do the same things. Okay, so here's where I am. The last two terms are at the bottom here, del IR minus del IR del VA minus del IR del VB. So what's this? Why is this here? Because the only contribution to the current balance of a FB is IR, or rather minus IR, because this is I in. Okay, I in is by definition that if you put current into this node, is by definition negative, so that's why there's a minus sign in front. So we have to account for that. So these are the only four terms we need to consider with respect to the Jacobian. Why is this important? Because now we have things explicitly in terms of current and voltage. We can now convert it to a mass flow rate. Okay, we can now convert it to a mass flow rate and a kinematic pressure if we want to do it for pipe. So for the mass flow rate, we have, let's say, the mass flow rate through the pipe, and this is the Jacobian we need to calculate. Okay, mass flow rate in the pipe over what? Differentiate with respect to, this is a partial derivative, with respect to the kinematic pressure at A. And then of course I want to put the units there, meter square per second square. Try as far as possible to put everything in SI, but we'll do the units part later. So this is kg per second. So I will not write the units all the way through, but at least I will have it once per page. Okay? So this is the equivalent. Okay. So when I say del m dot p, that's the mass flow rate through the pipe. Okay. So the bottom equivalently, you have to do different things as well. Del m mass flow rate through the pipe, del p a minus del m mass flow rate through the pipe, del pb, the kinematic pressure at B. So that is how we get from the Jacobian to put it in terms of current and voltage for the resistor. And that's why you have the R minus R and everything down here. So you see this is the conversion. Why this del FA del VA results in 1 over R minus 1 over R minus 1 over R and then 1 over R. Okay, for a resistor. This is where Ohm's law is obeyed. Okay. So converting that to a current and voltage differentiation, that will make it easy for us to convert it to this form as well for pipe. Okay, so that current 1 ampere will be equivalent to 1 kg per second. 1 volt will be equals to 1 meter square per second square in terms of kinematic pressure. So that's how we'll just apply these conversions directly. Okay, so that is the idea. So that's how I got from this part to this part, right? So the contributions to the mass flow rate at node A of this resistor is the mass flow rate of the pipe. So I'm switching from current notations to mass flow rates. Okay, and of course the contribution of mass flow rate to node B due to this resistor slash pipe is the negative of the mass flow rate of the pipe, or minus the current of the pipe of the resistor. Okay, so the contributions to the nonlinear resistor by this Jacobian are, as you see, I have already typed out all of this. so I will not need to, you know, put it, yeah, I'll not need to type it again. So I convert these currents and voltages into mass flow rates and pressures. Okay, so it's a 1-for-1 swap. As you see here, IR becomes mass flow rate of the pipe, VA becomes the kinematic pressure A, VB becomes kinematic pressure at B. So I think yes, we shall do a little bit of units as well. At least I'll put one here. Okay, meter square per second square, divide by okay, I think I had the units misplaced for the numerator, so let me change that before going on. CI bracket kg per second. Okay, now the units are right. At least you know what these are. Okay, a question is, how are we going to get this mass flow rate of the pipe with respect to the kinematic pressure based on our equations, right? The whole point of getting those equations out is so that we can find these derivatives. The mass flow rate of the pipe, they are PA. Now, as you see, if we keep going up, of course, we look at this equation. It's not very nice, in the sense that, you know, the friction factor, or rather, you see a dynamic pressure delta P right here. You have a dynamic pressure delta P right here. Okay, dynamic pressure is of course related to related directly to the so-called delta V, right? Yeah, so this is yeah, we need to get the dynamic pressure. We need to make things, well, if you want to do a direct derivative, we need to make mass flow rate the subject of the equation in terms of delta PA. Okay, well, of course, when we look at this is like not possible. How are we going to factorize out all the velocity dependent terms and the mass flow rate dependent terms? Okay, U square is of course dependent, directly related to mass flow rate. Reynolds number also, and all the terms inside also have something to do with mass flow rate, right? That's not going to be very viable. So you can see immediately there's a problem. How do we overcome the problem? So there are a few ways, of course. First thing first is to do numerical differentiation. Okay, you can do numerical differentiation, or I will exploit the fact. Okay, exploit the fact of this. Exploit this fact. Okay, dy dx equals to 1 over dx dy. And this will help us. This will help us with this issue where we have the mass flow rate of the pipe. We can actually do the derivative with respect to, instead of the pressure, we do it with respect to the mass flow rate, and there can be some level of explicit differentiation, then take 1 over that number. However, for partial derivatives, this may or may not be true. Okay, for partial derivatives, this may or may not be true. That's because the Jacobians they use partial derivatives, so flipping them on top of another may not always be true, because the partial and the total derivatives are kind of slightly different. However, let's take a look at our equation again and see whether we can reduce this total derivative or partial derivative to a total derivative. Okay, so the only two things we are concerned with are the pressure drop, or rather kinematic pressure change, and the mass flow rate, which is kind of directly related to velocity, right? Of course, we can of course change the Reynolds number to velocity, but I think it's easier to change the velocity into some form of Reynolds number, and then we get the mass flow rate from there at the end of the day. Because dimensionless numbers are easier to work with, we do not need to concern ourselves with units. Okay, so we'll try to keep it in a non-dimensional form. Okay, so that's the idea we want to go forward with here. We try to put it in non-dimensional form. Okay, so Reynolds number has something to do with the mass flow rate, and if we take a look at the Reynolds number, okay, for a normal pipe flow, mass flow rate will always change. depending on the pressure drop, but everything will also be sort of the same with respect to pressure drop. Like diameter of the pipe, you don't expect the diameter of the pipe to change very much, if at all. Cross-sectional area of the pipe, and of course viscosity of the fluid shouldn't change too much with the pressure. Okay, this is for, of course, incompressible fluids, right, that you don't have compressibility effects. You don't take those things into account. So during a flow situation where you keep changing pressure, only mass flow rate should change, nothing else should change. So all of these are pretty much constant. Okay, what other terms are there in there? Okay, you have the roughness ratio. The roughness ratio, of course, should not change with pressure. Okay, roughness ratio should not change with pressure. Reynolds number, the only reason it will change with pressure is because of the mass flow rate. And density should not change with mass flow rate. I mean, density should not change with the pressure, the change in pressure, because we are looking at more or less the incompressible fluid. L/D ratio also shouldn't change so much, if at all. So all of these things are pretty much constant. We can reduce that total derivative into this partial derivative, we can convert it almost into a total derivative. Okay, so that's for a pipe of constant dimensions, constant fluid properties. Okay, except for fluid properties as in viscosity and density. Everything else should be the same. Okay, so thankfully for us, we only need to concern ourselves with the Reynolds number and delta P, which is the kinematic pressure drop. Okay, so it's relatively straightforward. If one knows the central difference approximation to approximate this derivative, we can use numerical simulation, or not simulation, methods, numerical differentiation methods. So if we look over here where this rho is, if we divide this whole equation by the density rho, we will have kinematic pressure on the left hand side, U square on the right hand side, and of course we will try our best to non-dimensionalize this U. We'll convert it into some form of Reynolds number, and then we'll move all the terms to the left hand side and non-dimensionalize the left hand side as well. Okay, I think I'm missing a number 2 in there somewhere, right? 2 Reynolds number to the 12, 1 over, and then for L/D here. Yeah, I'm missing a number 2 here. So let me reintroduce that number 2. Okay, I'll put the number 2 over here, and that should be it. Hopefully, yeah, no more careless mistakes. No, I do tend to have careless mistakes. Okay, so nevertheless, the constant of 2 doesn't make too much of a difference in terms of the differentiation technique. Yeah, doesn't make too much of a difference in the differentiation technique. So just need to change that later on. I think my documentation is kind of off. I'll do it as we go. Okay, so I'm going to convert all of these things here into sort of a, yeah, I'm going to convert all of this into a dimensionless form, so it's easier to deal with. Okay, and of course the reason why I showed this laminar regime and the turbulent regime earlier is because eventually at the end of the day we need to differentiate things. We need to see, maybe in limiting cases we do not have to do so much calculus, alright, but that was just a thing. It's easier to do the differentiation here. We have a mass flow rate with respect to pressure drop, so we can do del MA del P del delta P right here. Very easy. Okay, for this part over here, also very easy to do this pressure drop differentiation, excuse me. Yeah. But yeah, unfortunately our case is not that simple, so we'll have to do some trickery. Okay, so we start off assuming that we know this value. Okay, assuming we know this value, we want to of course obtain this value, delta M pipe delta PA. or partial M pipe, partial VA, PA. Alright, so I will use first the chain rule right here. Chain, if I'm not wrong, yeah, chain rule. Chain rule right here will help us to include the variable PA into our derivatives here. So d delta P del RE is, okay, this is our starting point, because we can easily so-called differentiate this equation. Yeah, I can differentiate the above equation right here. We can differentiate the above equation right here with respect to the Reynolds number, and then we will get some we will get ourselves a little bit of, yeah, we will get ourselves a nice numerical answer. It's a constant. Okay, so we do the chain rule to introduce back our dPA at the bottom and at the top, and of course not just that, I want to reintroduce the mass flow rate of the pipe into the chain rule. Yeah. Alright, so anyway, yes, here's what we have. Okay, important. Okay, the delta P, yeah, we introduce PA back in. Okay, so this is the derivative we can get. This is the derivative we want. So I need to introduce it in here somehow. So the way I do it is to first introduce PA to this derivative to split up these two using chain rule. And then the second derivative right here, dPA dRE, dPA dRE. Okay, this one I will split it up again using chain rule by introducing the mass flow rate of the pipe in. Okay, so this is how I split it up. Then what I want to do now is to make dPA dm pipe the subject. So dPA dm pipe will be this term over here, this term in the center here. I will shift all the terms to the I'll shift all the terms over to the other side, and then I'll make this the subject. So we get this resulting equation, d delta P over the RE, okay, divided by d delta P dPA times the m pipe dRE. And to get the total derivative, we just flip it over on its head. The m pipe dV PA equals to all of these terms on the right hand side. Okay, so I just made the denominator the numerator and the numerator the denominator, is just switching it around. Okay, so to obtain a partial derivative, we just set PB as constant, and then we start working from there. Okay, so the only thing that we have to do with this the delta P dPA, if we want the partial derivative, we just set PB as constant. PB will only appear in this d delta P part. Okay, d delta P part. So other than that, you don't really even need to do anything here. Again, d delta P dRE, this is the term at the bottom. It's calculated either numerically or analytically, so don't touch that term. So that term is being used to divide the top term. Okay, so just set PB as constant and work from there. So delta P equals to, of course, PA minus PB. Okay, so let me do delta P equals to PA minus PB. So this is the pressure drop. Of course, sign convention wise, yeah, that should be correct. Yeah, note here. Okay, delta P refers to kinematic pressure drop, not pressure change. Okay, pressure change is final minus initial. Okay, final. Okay, let me put this here. and whereas pressure drop is initial minus final, right? Right, so there's one more step. Okay, so this step is the non-dimensionalization step, because the whole equation is not properly set in Reynolds number just yet. So I want to substitute this half rho u square term in terms of Reynolds number. So I just have the Reynolds number definition. I make u the subject, okay, to substitute half rho u square out. So it becomes Reynolds number times mu over rho d. So I bring the mu up, the rho d down. That should be it. Substitute the result in. So the u square becomes Reynolds number mu over rho d, whole thing squared. Then I start cancelling terms. Okay, what terms do I start cancelling? Okay, the first thing I bring out is to bring out this Reynolds number square from the inside to the left hand side. Okay, Reynolds number from the inside to the left hand side. So that's where I get from the first to the second step. So remember fanning friction factor here. Okay, I will just make it clear again. Fanning friction factor okay, here is actually just a function of Reynolds number. Of course, there's other things as well, like the surface roughness ratio and everything else, but for a fixed pipe, friction factor will only depend on the Reynolds number. Okay, so after this I start cancelling other terms as well. So this F equals to the F fanning Reynolds number. Okay, so I'll just put a note here, just okay, maybe I'm overkilling it. So okay, never mind. Every time you see F here, it's F fanning RE. This is the thing here. Okay, so every time I have this F is this thing here, so I start cancelling out the terms even more. Wait. Yeah, so what's the first thing I do? What did I do here? It's as if I did not even do my steps properly. Yeah, looks like this step is exactly the same as this step. I can't even tell what the difference is, so I better cancel out those terms. If not it's like redundant. Okay, so after this step, I square all the terms in here and then start cancelling out the terms. Okay, I square everything here, and then that's why there's all the power of square inside. I bring the rho up, okay, to convert this dynamic pressure to some sort of kinematic pressure. So I change from uppercase P to lowercase p. And the other thing, I convert this dynamic viscosity divided by the density into kinematic viscosity. Okay, and then the d square term, I bring it out here. Well, I can bring it out later. So we have sort of a collection of non-dimensionalized variables. Because friction factor is dimensionless, Reynolds number square is dimensionless, for L over D is dimensionless. So this collection of terms here is some sort of non-dimensionalized pressure. Is that, and my question after that is there any existing non-dimensional number that matches this sort of collection of variables? Yeah, I guess I'll talk about that more in the next video. So I'll see you later.